Record. Okay. So let's get started. So let me go to Notability. Math 148. Okay. So again, a reminder, quiz due in 7 hours, I guess. So, okay, so let's get started. So today we'll be, constructing R pretty much. And then we'll be doing a lot of questions from the book because I feel in this case it's really the only way we're gonna it's the easiest way to understand things. So let's let S be a non-empty subset. So non-empty subset of R. So hopefully this is clear. If S has a largest element, I'll write ELT for element S naught. S naught is the maximum of S and S naught, and basically we write S, this is like shorthand notation. S naught is max S. And similarly, if S contains a smallest element, S, I'll just leave it at that. Then it is called the minimum. And we denote, denote by min S. So, I mean, examples are, if I gave you something like this, right? The max of S is 10 and the min of S is like 1, right? And not every set, obviously your set has, something like the integers or rational numbers, they don't have a maximum, right? So, because integers just keep going on forever, like to infinity and negative infinity. Now, there is something we have to work with, right? So if S was something like this, right? Clearly the max of S is 1, right? But the min of S, like you want to say it's 0, right? Because the terms are going to 0. But the point is 0 is not in the set, right? I mean, the set contains like numbers going to 0, but not 0 itself. So this does not exist, right? So basically we want the notion of, like to say there's like a lower bound, right? So definition, let S, again, non-empty subset of R. So if there exists a real number M satisfying every element in S is smaller than it, so for all S and S, then M is an upper bound. And similarly, if there exists a real number M satisfying, so here we want S is bigger than, right? So M is smaller than every element in S. Then M is a lower bound. So we basically say, so if there is upper bound, if M exists, we say S bounded above, right? And if such M exists, S bounded below. And we say S is bounded if S bounded above and below, right? So hopefully this is, very intuitive for now. So if we go back like up, right, clearly the 0 is a lower bound, right? But there's a problem, right? If you read the definition right now, -1 is also a lower bound, right? I mean, any number before 0 is also a lower bound. In fact, all of these are lower bounds, right? I don't know. You could pick your favorite number, -3.5, so on and so forth, right? Like basically, as long as you're smaller than every number in your set, you're a lower bound. But like there's something special about 0, right? The terms, like it's like the sort of like the biggest one, right? The biggest lower bound. So basically we're gonna get into notion of like inf and sup. So here, let me again. So there's a lot of definitions here, but hopefully it's all intuitive. So S again, non-empty. So A, if S bounded above, and S has least upper bound, call it sup S. So sup is for like supremum S, right? Stands for supremum of S. And if S bounded below and has greatest lower bound, so the biggest lower bound, call it inf of S, and it stands for infimum. So above, although like if you look above 0, -1, -2, -2.5, they're all lower bounds, but like 0 is the inf, right? It's the biggest one out of all of it. So, okay. So we'll do examples of finding like infimum and supremum of sets like in, soon. But let's go over the important part. So completeness axiom. So basically, how we create R is we consider sets in Q and take all its supremums, basically. So R is complete because every non-empty subset S of R, so S of R that is bounded above, and similarly you could do bounded below, that is bounded above has a least upper bound. Upper bound sup S, and it belongs to R. So basically what we're doing is we consider any non-empty. So how do we get root 2, right, from Q? Well, we take this set. So R in Q such that 0 less than R less than root 2, right? This is my S. So basically R is, I add in all the supremums of like of any set you could think of, in particular like this set, right? The sup of this set is root 2, right? Root 2 is not in Q, right? We proved that using rational zero theorem, but it's certainly the supremum. Remember, supremum doesn't need to be in your set. That's the difference between sup and max, right? So sup is like, even if your terms go to it, like here, there's like a sequence of going to root 2, but it never hits root 2. So that's the idea, like that's how we create R, basically. Okay, so now 2 more properties, and then we'll just do prompts so we all get used to, all these new definitions. So Archimedean property. So this is actually very useful. So if A is bigger than 0, B is bigger than 0, there exists n such that n times A. So let me just write positive n, positive integer n such that n times A is bigger than B. Hopefully this is clear, right? Like no matter what two positive numbers you give me, I could find a number such that when I multiply it, I eventually become bigger than the other one, right? So like, for example, if A is like 2 and B is like 1 million, my N could be like 2 million, right? So 2 million times 2 is bigger than 1 million. So hopefully that's obvious. So here, there's an important thing we're going to use. It's called denseness of Q. So this is a very important result, basically. You'll use this in 140B if you plan on taking it. Because I know because I'm also TAing 140B. So, okay, so let's call this star. So if AB is in R, A less than B, there exists rational R in Q such that A less than R less than B, right? So hopefully you believe this, right? If I give you any two numbers, like not equal, but any two numbers, you could find a rational number between them, right? Like if you gave me like 3 and 4, like 3.5 would be a rational number between them. So let's start doing problems now. So we're going to be doing a lot of questions today. So Kenneth Ross. So and I noticed it's good that we do questions because I think your professor assigns questions from the book. So it's good we do some examples. So completeness axiom. Yeah, okay, here we go. So let me just pick the important ones. So yes. Okay, so what we're going to do is consider 4.11. So let's practice how to use denseness of Q since I just went over it. So let me read it. Consider A, B, and R, A less than B. Use denseness of Q to show there are infinitely many rationals between A and B. So basically we'll be sort of applying it inductively, right? So, whoa, what happened? So is 4.11? Is it 4.11? Yeah. Consider A, B, and R, A less than B. Basically show there exists infinitely many rationals in AB. Okay, so how are we going to use denseness of Q? So with denseness of Q, we could certainly get one, right? We could get one rational between AB. So by star, there exists R1 in Q such that A less than R1 less than B, right? That's just the statement of denseness of Q. But now, since R1 is bigger than A, we can consider this smaller interval, right? We can consider this. And then now we apply denseness of Q again with like A being A and our B being R1, right? So here, by star, there exists R2 in Q such that A less than R2 less than R1, right? And then hopefully you all see the process, right? Now you consider A to R2. So by star, there exists R3 in Q such that A less than R3 less than R2. And it's clear from the inequalities, R1, R2, R3, they all can't be equal, right? So ... right? So you basically get an infinite. So continue inductively to get infinitely many rationals, right? So hopefully that's a good starting problem to do. So let me show you the usefulness of Archimedean property. It sounds like really dumb, right? And very obvious, but it gets very useful. So let's do example 4.10. Let me pull up the problem. So 4.10 is prove if A is greater than 0, there exists n in n such that 1 over n is less than A less than n. So this looks very similar to Archimedean property, right? Because Archimedean property is show something is bigger than, there's some n such that, you know, you're bigger than or smaller than some other number. So let me copy the prompt. So given A greater than 0, there exists, show there exists n such that 1 over n less than. So I'm going to change this to B, okay? Just for, whoa, what happened? This is B. Yeah. So given B bigger than 0, there exists, you know, n such that 1 over n less than B less than n. So how are we going to do this? So certainly if B is bigger than 0, right, I can consider interval 0B, right? Because B is bigger than 0. Now I can apply density of rationals, right? So there exists R. I'm going to call, R is rational, right? So let me just erase this. So by star again, there exists R equal to, let's say, P over Q, yeah? And we might as well just say it's reduced, right? So again, by reduced, I mean, instead of 2 over 4, it's 1/2, yeah? So there exists R equals P over Q such that 0 less than, I'll write P over Q from now on instead of R. Right, so this is by density of rationals. Okay, so now I want a 1, right? I don't want a P on top, but it's certainly true that the smallest number P can be is 1, right? So I could certainly say, okay, consider this now. So certainly this is true, right? Less than or equal to. So I might as well consider just this, right? The reason being is I need a 1, right? I need 1 over n, not like P over n, right? Okay, the problem is if you invert it, it need not be true that it's bigger than, you know, B, right? Because the inequality goes like this, right? Q is bigger than 1 over B. It's not bigger than B, right? So you need to somehow adjust this a bit, right? Q might not be what you want, right? So an example to think of is like 0 less than a half less than 3, right? So it's not true that 2 is bigger than 3, for example. So I'm taking B to be 3 and my Q to be 2. So we need something, so in that case, we needed something smaller, right? So how are we going to get this n, right? Well, so obviously our Q might not be our n, right? So we need something on this side. So that's where Archimedean property comes in. So by Archimedean property, there exists n such that n times 1 is bigger than B, right? So why do I do this? Well, if we look over here, how am I applying Archimedean property? I'm taking my A to be 1 and my B to be just B. That's why I changed the notation to B. So you won't get confused. So I'm using the Archimedean on A equals 1 and B being B. So there exists n such that n times 1 is bigger than B. But then we are done now, because now we say let S be the maximum of Q and N, right? Then certainly this is true, right? Hopefully you all agree with me. So let me just write this. So this part, and then B is going to be smaller than N, which is smaller than S. So let me explain this part. So from here, right, we had this. Now S is the max of Q and N. So in particular, S is bigger than Q, right? And when I put S in the denominator, it's certainly smaller than 1 over Q, because I have a bigger denominator. So this side holds. Now the other side, B is smaller than N, but S is the maximum of Q and N, so S is at least N, right? So I guess I need an equal to sign. So let me put this. Yeah, it should be less than or equal to. But in any case, you're gonna get this, right? 1 over S less than B less than S. And then you are done. Yeah. So
I'm still confused about the process of let S equal to max Q and N. Why would we do that? S equals to max this one.
So if you don't, what is your candidate for what is your candidate for this? What do you want your candidate to be? What do you want your n to be? Let me just change the variable since I used n. Show there exists m such that. So I'm saying what do you want your m to be if it's not s? Is my question. So it can't be Q, right? I mean it could be, but like Q as of up to here, up to this line, we don't know if Q is bigger than B. We needed a number. We needed to find a number that's bigger than B, right? So to find a number bigger than B, I use Archimedean property. So n is bigger than B, but it need not be the case that 1 over n is less than B, right? That's I only know 1 over Q is less than B. I don't know 1 over n is less than B. For example, if B was like a half, then 3 is bigger than a half. If n is 3, then 3 is bigger than a half, but 1 over, oh, I guess this is a bad example. Take B to be 1/4. 1/4. Then 3 is bigger than a fourth, but 1 over 3 is not less than 1 over 4, right? For example. So basically what I'm saying is, this part gives you the bigger than, the Q gives you the less than. So I need to somehow combine those two to get both sides, basically. If that makes sense.
Oh.
Yeah, because a priori, like it need not be the case that you get basically you need the same number on both sides. If this was like an M and then like a K, then it's easy, right? The point is that they want the like this M over here to be this M over here. Yeah, that's the hard part. We need something like S and S. Yeah. Okay. So yeah, so basically, if you think about it, this will not work, right? Might not work, is what I'm saying. Right. I gave the example above, and then from here, I'm saying this might not work either. So we need to somehow combine it in a sense. So okay. So let's continue. So the next thing I do will be pretty important. So please pay attention. So it's proving stuff about infimum and supremum. So 4.9 is what I want. So 4.9, it says like prove 1 and 2 and like use corollary. I feel the way the book, writes it is very confusing for people. So I'll try to make it very simple. So 4.9, prove infimum of S is negative sup of negative S. So there's a negative sign here. So we're going to assume these are finite, right? We never really introduce like infimum and supremum to be infinity yet. I think that's the next section, right? The next section is like, yeah, the symbols plus infinity and minus infinity. So as of now, we only constructed the real numbers, right? We never introduced what infinity and negative infinity is yet. So the book sort of assumes like this thing is finite. So, okay. So how do we do this? So this is actually very simple. So before I continue, hopefully you all know like S is a set, non-empty, subset of R. Negative S is what you think. It's negative S it's a set of negative S such that S is an S, right? It's just this set. So let me kind of sort of explain how you would prove this. It's actually not that hard. So just follow me really quick. So how would you prove two numbers are equal? So the way to tackle this is if I show a number is bigger than or equal to some other number and also smaller than or equal to some other number, that same number, then they have to be equal, right? Like if A is less than or equal to C and also bigger than or equal to C, then A has to be equal to C. So that's the approach we'll take. So let alpha equal inf of S. Now, so this is where you all need to know the definition. So infimum is what? It is a lower bound and it's the greatest lower bound, right? So in particular, it's a lower bound. So by definition, alpha is less than S for all S in S, right? That's what it means to be a lower bound. You're smaller than every element in your set. Okay, now I want something with like negative S, right? So let's do minus alpha for all S and S. So sorry, I need to change the sign. So, okay, so I just multiplied by -1, so nothing changed. Now this is the thing you have to convince yourself. If S runs through every element in S, right? This is for all S and S. Then negative S will run through all elements in negative capital S, right? So you could say it's greater than equal to T for all T in the set negative S. So is everyone clear with that? So this is probably like actually the most confusing part. The rest is very simple. So again, if S runs through little s runs through all elements of big S, then negative little s runs through all elements of big negative S. So basically, I could write negative alpha greater than equal to T for all T in the set negative S. Okay, now you're pretty much done because what does this mean? So what is negative alpha here? If it's bigger than every element in negative S, this so line 3 by definition means negative alpha is an upper bound, right? Upper bound of negative S, right? I mean, it's bigger than or equal to every element in it, right? So negative alpha is upper bound. But what is supremum? Supremum is the what? The least upper bound, right? It's smaller than all the other upper bounds. So negative alpha is less than or equal to sup of negative s. Does every, oh, sorry, greater than. Yeah. Actually, it's big, sorry, it's bigger than. Right? Sup of negative s is the smallest upper bound, right? So negative alpha has to be bigger than it. Because negative alpha is just an upper bound, but sup is the least upper bound. And then we move the negative to the other side. So greater than, if I move a negative, it becomes less than, right? Divide by -1. And now what was alpha? Alpha was inf s, right? So we showed less than or equal to. Right, so I told you the goal is to show less than or equal to and then bigger than or equal to, right? So right now we showed like the less than or equal to case. So infimum of s is smaller than or equal to negative supremum. So now how do we get the other way? Well, we go backwards, right? So let beta, so let me box this, right? So let beta be sup of negative s now. And now we go backwards. So by definition, this means what? Sup is an upper bound, right? So beta is bigger than or equal to t for all t in negative s, right? This is a property of sup. It's an upper bound. It's the least upper bound, but I'm just using the fact it's an upper bound. So it's bigger than or equal to t for all t in negative s. And then again, you negate it. So when I negate, I move the sign, right? So same argument, right? If t runs through every element in negative s, negative t runs through all elements in s, right? Because negative of negative is positive. So this thing is less than or equal to s for all s in s. So same argument of how I went from like 2 to 3 right here. Okay, now we are pretty much done because what does this say? This let me write 4, 5, 6. So line 6 by definition, right, means negative beta is a lower bound of S, right? Because I'm smaller than every element in S. So that means, but what is infimum? Infimum is the greatest lower bound, right? So negative beta is going to be smaller than or equal to infimum of S, because negative beta is a lower bound, but infimum is the greatest lower bound. And then you're done, because what was beta? Beta was sup S, right? Sup negative S. Right, so from these two inequalities, we get that they are equal, right? So when you see this, like other questions similar to this, you always tackle it this way, right? To get the, basically, if you have infant sup, you use the fact that it's like the greatest lower bound and the least upper bound to get the two inequalities, and then you show they're equal. So that's generally how like these sup inf problems go, as far as I know. So okay, any questions so far? Okay, so finally, let's practice, finding inf sup max and min. So they have really nice examples. Like this is really nice. Like 4.1, they have like a whole set of examples. So okay, so let's say m first. 4.1 m, the set of R and Q such that R. 4.1 m, the set of R in Q such that R squared is less than 4. So what I want you all to figure out is this. What is this? This is S, by the way. Okay. What do you guys, or what do you all think about the maximum? Is there a maximum here?
Hello, is that R or Q on the second line of 4.1? R belongs to what?
Rational numbers. So
Okay.
yeah. So what do you all think? Is there a maximum?
No.
No, right? Because you could find like arbitrary arbitrary number of elements going to the number 2, right? Because 2 squared is equal to 4. But like it's not in the set, but you could find numbers getting close to it, right? Like 1.99999 is like getting closer and closer to 4, but it's still smaller. The square of it is still smaller than 4, so does not exist. Okay, what about
when we have this kind of questions, like we cannot find a kind of a exist number for this thing, but can we find for example, this one, the 2, we cannot pick 2, but how about 1? Is
uh
a 1 is a rational number,
sure.
and it's smaller than 2. So why we can't pick 1?
But it's not the maximum, right? I could find you a bigger one, like 1.5.
Oh,
So I'm saying I could find you an infinite sequence that like all these numbers square to something less than 4, right? The square of this is less than 4. The square of this is less than 4, right?
gotcha.
Yeah. So there's no maximum because I could just keep finding something bigger, right? I could just keep adding a 9. So yeah. Okay, so what about minimum? So when you square a number, can it be negative?
No.
So the biggest r squared can be is what? I mean the smallest r squared can be, sorry.
0?
Yeah, and do you attain 0 in this case? Yes, right. I mean 0 is rational and 0 squared is 0, right? So 0 is a minimum. Okay, now what is the supremum?
Is the supremum 4?
Not 4.
Two.
It's r, not r squared. No, just
2 then,
like
right?
yeah, it's 2. Yeah. So don't be confused. Like it's the set of r and q, right? Not like the r squared is just like a condition. So, and infimum is in this case, if a min exists, the infimum is the min, right? I mean, there's.
So why is the main exist?
So I'm saying obviously 0 is in the set. Do you agree?
Yeah, but it can be negative.
Oh, we're I take it back. Yeah, you're right. No. Oh yeah, you're right. My bad. I was thinking of the image. Yeah. Sorry about that. I made the same mistake as someone else. Yeah. So in this case, it's the opposite. You could find a negative 1.999, right? An infinite sequence the other way, right? So
Yeah, so it does not exist, right?
yeah. Sorry. So sorry. But infimum is okay. In this case, what is the infimum?
It's negative 2.
Yeah. Good. Because this thing, whoa, what just happened? Give me a moment. I don't know what just happened. Okay, actually, let me let me exit out and go back. I don't know what just happened. So, okay, great. So yeah, so because this sequence goes to -2, right? And like this thing goes to 2, but it doesn't approach it. So let's continue. So let's do something harder. So, okay, yeah, I'm gonna do something a bit harder. So intersection. Let's do I, right? Something a bit harder. So intersection I equals 1 to infinity. Are you all familiar with n equals 1 to infinity? A bracket -1 over n, 1 plus 1 over n. So I'll change that I in just a moment. Are you all familiar with intersection and like what that means?
Yeah.
So like, okay, good. So here, the first thing you want to do is figure out what is in this set, right? We can't really work with anything, you know, if this is S. Like we can't really work with it unless we know what's in the set. So in this case, my first question would be, can any negative number be in the set? So let's say I picked a negative number, like -1/4. Can that be in my set? So remember, we're intersecting, right? So if I chose, like, let's do an example, chose -1/4. What about n equals 5? When n is 5, it's this this interval, right? Does everyone agree?
Yep.
Does this interval have -1/4?
Yes.
No.
No.
It doesn't, right? Because
Yeah.
Yeah.
so are you all convinced that the idea is because -1 over n goes to 0, I can't have any negative numbers? Do you all agree? Hopefully you
But
can.
if we let n equal to 3, we can include 1 over. 1 over. You
But
choose 1 over.
but we are intersecting, right?
Oh.
Yeah. Once I find one, intersection means if I have to belong to every single one of the things, right? If I'm not in n equals 5, I can't be in the intersection, right?
Okay. My bad.
Yeah. Okay. Now, so we agree we can't have negative numbers. Can we have 0? So basically, no.
Yes.
Yeah. No matter what n I choose, 0 is in here, right? Does everyone agree? Good. So now, what about the number? Any number bigger than 1? Can I have a number bigger than 1?
No.
No, right? Because let's say I had, like, 1 plus, I don't know, 1/2, right? Then you just choose n equals 3, and it's not in this interval, right? So basically, I can't have any number bigger than 1. That the idea is because 1 over n goes to 0. So can I have the number 1?
Yes.
Yeah,
Yeah.
I can, right? So 1 is in this interval. And finally, can I have any number between 0 and 1?
Yes.
Yeah, right. I mean, that's certainly possible. So this is actually a shorthand notation for the interval 0, 1. It's just a fancy way to write the interval from 0 to 1. So can you all figure out what the max is now? The max is what?
The max is 1.
Yeah. What's the min?
It's 0.
Yeah. Hopefully you can all see this, right? So yeah, this one is just figuring out what intersection means, right? So, all right, let's do one more and then call it a day. So let's do some, yeah, let's practice, since most people are sort of struggling, let's do R, yeah, another intersection question. So intersection infinity to n equals 1. So 1 minus 1 over n, 1 plus 1 over n. What is this? So obviously this thing, okay, so the question, let me ask the question. So question 1, can I have a number smaller than 1?
No.
No, right? Because let's say I had like 9 over 10, then like 1 minus, you know, 1 over, like, for n large enough, right? And I think n equals 11. This is 10 over 11, right? And 10 over 11 is bigger than 9 over 10. So the idea is 1 over n goes to 0, right? So this term is approaching 1, right? So if it approaches 1, any number smaller than 1, eventually I'll pass it, right? Okay, so question 2, can I have a number bigger than 1?
No.
No.
Same idea, right? This is approaching 1. Okay, so that no. So hopefully you all know what the last question is, right? Can I have 1?
Sure.
Yes.
Yeah, I can certainly have 1 because 1 is in every single one of these intervals, right? So this thing is actually just the set 1. So if this is S, then the max of S equals sup of S equals inf of S equals min of S, right? It's just 1. Yeah. So hopefully this it makes things clear, like, you know, how to calculate sup, max, inf, and so on and so forth. Okay. That's all for today. So again, make sure you do your quiz. It's due, I guess, in around 6 hours, or I mean, yeah, 6 hours. So make sure you do it.
Thank you.
No problem.